Chapter 6 here, we're going to be looking at ionic and molecular compounds, or what I would call covalent compounds. I will also say that although it's okay to use the word compounds a lot of times, I tend to think of ionic as compounds and covalent bonding things as molecules. And if I want to refer to both together, I'll use the word substances. I think it also, by using two different words, compound versus molecule, makes it a little bit easier to tell which is going on. Some textbooks will split these into two separate chapters. Others will have them combined into one. And unfortunately, it does cause a little bit of confusion as to how to identify which is which. And we'll get into that here. But do keep in mind we're covering two different types of bonding, which involves two different ways of naming substances and two different ways that the electrons behave, whether electrons are transferred or shared in these two different types of bonding. And so the first several sections are going to look at ionic, and then after that we'll look at covalent or molecular substances. So getting right into 6.1 here, we're going to look at ions, which will set us up to being able to do ionic bonding. The upcoming slides are going to get into this. This is just your introductory slide. However, I think it's got pretty much everything we need for this one. So when you lose electrons, because electrons have a negative charge, if you're getting rid of negative charge and you started out neutral, because atoms start out with an equal number of protons and electrons. Remember that when we were talking periodic trends and patterns on the periodic table and atoms themselves, we said that the number of protons is going to equal the number of electrons, which equals the atomic number. However, I mentioned then that is the usual number of electrons that atoms can gain or lose electrons, and as they do that, then their protons stay the same, but they end up with a charge. So, for example, if we have carbon has 6 electrons total and 6 protons total. Well, it turns out that carbon can gain electrons and end up at 10 electrons, or it can lose electrons and end up at only 2 electrons. Well, when it does that, if it gains extra electrons, it's gaining negative charge, then it's going to end up with extra electrons. At 10 negatives, 6 positives, we end up with a 4 minus charge. Versus if it loses 4 electrons, then it's got 6 protons and only 2 electrons, and then it ends up with a 4 plus charge. And so it sounds backwards that when you lose something, you end up with a positive charge. And that when you gain something, you end up with a negative charge. But you have to remember that electrons are negative. And so then what ends up happening is when we get into having ions, then we can start to form ionic bonds, because you know that opposite charges attract. And we mentioned that briefly previously as well. Now, despite introducing ions there, they then kind of give you a decent summary table here of the different types of things that we have. Ions that form ionic bonds, and a classic example of this is Na and Cl ions, Na plus and Cl minus, or sodium chloride. Also known as table salt. The classic example of a covalent molecule is water, H2O. This one here is propane. And you may ask yourself, why do they have 2 examples of this one and only 1 example of that one? Part of it just has to do with how common they are, that we will work with more ionic compounds in this course, and yet there's probably more molecular compounds in the world, especially considering that if you go on to take 111 or any kind of organic chemistry, it's all about molecules and not about ions for the most part. But it turns out there's such a thing as polar covalent and nonpolar covalent. And both of these would be molecules involved, or I would describe it as the particles are atoms forming a molecule. But we'll get into polarity later on towards the end of this chapter. Anyway, when it comes to bonding, atoms want to have an octet, a full outer shell of electrons, a full outer energy level, and that is normally going to involve 8 electrons. It's where the oct and octet comes from, and this is known as the octet rule. I will point out that hydrogen is your major exception. And that's because if we go back to the electron arrangements or electron configurations, that first energy level can only hold 2 electrons. So hydrogen starts with 1 electron, and it wants to end up we'll still call it a full octet for it. But a full octet for it is only 2 electrons, or it can actually get rid of that electron and end up with 0. And then the outermost energy level is empty. Ionic bonds occur when you have valence electrons from a metal get transferred to a nonmetal. That's going to give since we're transferring electrons, it'll give the metal a positive charge, the nonmetal a negative charge if we're transferring multiple electrons, and they'll end up with multiples. And as a side note, when we have a charge, we put the charges as superscript here. And a lot of times chemists will do the number than the sign. And so we'll write it as a 2 minus charge instead of a -2 charge. Both are acceptable, but just because you're going to see that, I want to mention it. It's also how I was taught and how I will write them out. Always, even if the textbook is doing other things, I don't remember exactly which one your textbook does. Covalent bonds instead share valence electrons, and then that is how they end up with a full outer shell. Between those two, covalent bonds then are always going to result in the outer energy level, or outer shell as they keep calling it, filling up. For ionic bonds, the outer one can fill up, or it can empty out. And if it empties out, then if you go back to electron arrangements, if we just take sodium, which was an example a moment ago from the sodium chloride. Sodium has an atomic number of 11, so it normally has 11 protons and 11 electrons. Those 11 electrons had the arrangement of this. Well, it could, theoretically at least, gain 7 electrons. And that would fill up that energy level, and it would have a full outer shell at that point. However, another option for it, and it turns out that this one is easier, and if you just think about it, numerically it's easier, it could lose 1 electron. Well, if it loses that 1 electron, then it still has a full octet because it had the prior energy level filled up. That's that Aufbau principle that we fill up one energy level before we start filling another. So then its outermost energy level is a full octet. I intentionally chose carbon as my example a moment ago because carbon is right on that boundary where it has 4 electrons in its outermost energy level, and if it wants to empty that out, it would be losing 4. However, it could also fill it up by gaining 4. And so it's right on that boundary where it could do either. In general, it's as simple as that. If the number is above 4, then it's going to tend to gain electrons. If the number of valence electrons it starts with is below 4, it's going to tend to lose them. Essentially, which one do I have to move the fewest number of electrons? For example here, we're just going to use fake symbols, fake elements here, metal and nonmetal. With ionic bonding, what will happen is that metal will lose an electron to the nonmetal, and the nonmetal will end up gaining it. And so then you can see that transfer here. Well, that loss of an electron caused the metal to end up with a positive charge. The gain of electron caused the nonmetal to end up with a negative charge because they had an equal number of protons and electrons to begin with. So now if on the metal here, we lose 1 electron, then we're going to have more protons. Whereas on the nonmetal, if we gain 1 electron, then we're going to have more electrons than protons. And so that's what causes the charges, and then opposite charges attract. And we end up with an ionic bond. When it comes to sharing, what will happen is elements will have a lone or unpaired electron, and that electron will become half of a shared pair of electrons. And so then you'll notice each of these had 7, which involved having 1, as we looked at previously with the Lewis models going around and pairing them up properly, results in there being these gaps here, and then those gaps get filled by the neighboring electrons. And so then we end up with this here, which is called a shared pair. And I just lost all my ink trying to fix a typo there, but it's not a big deal. This here is what we now call a shared pair of electrons. So we went from unpaired to them being half of a shared pair. And as a side note, these here are lone pairs, sometimes called unshared pairs of electrons, and usually they will stay that way. And although this section here says it's about ions, it's really been so far a compare-contrast ionic and covalent bonding and what's going on. Now we're going to get into just the ions and focusing on ionic bonding itself. And so you can almost think of this as like a section 0 as an introduction to the whole chapter.